All right. So right here is my depiction of a normal main sequence, right? So I'm gonna say main sequence. Let's give me a few colors here. Let's say pink is gonna be helium, and yellow is going to be hydrogen. So inside our main sequence star is we have all this hydrogen in the center that's burning, right? And this is the rest of the core around it. That's not that good. Hold on. All right, whatever. Here we go. So that whole star is made out of hydrogen, basically, right? So the whole star is hydrogen, and it's able to fuse hydrogen inside its core. So right here, it's fusing. Fusing hydrogen. All right. But what happens as it starts to run out of hydrogen? Right? As it starts to fuse hydrogen, it turns it into helium. So now what our core kind of looks like is now you have this bit of helium in the center, surrounded by your core of hydrogen that's still burning, right? This is the hydrogen that's still burning. And the rest of the hydrogen is still here. But you see, now our core is different. We have fusing, that's not that good. Fusing hydrogen. Using hydrogen, and this is our helium deposit. And that's where all the helium from the hydrogen is being put at, right there at the center of our star. Right. What happens once that hydrogen starts to run out? As we saw from the video, right, you see the size of our star starts to go from this size to something a little bit bigger. And the reason for that is that our core becomes mostly helium, right? Most of that helium is now stuck inside the core. And you have just a very fine layer of hydrogen that's still fusing. All right. So, and then what we have is a hydrogen shell around it. It's also fusing. So hydrogen shell. And this is our hydrogen core. And our helium deposit. Right? Helium deposit, hydrogen core that's starting to run out of hydrogen, and then our hydrogen shell. That's why our star begins to get bigger. Then what happens? After enough time, what basically happens is the core gets even smaller because now, after you completely run out of hydrogen, right? Imagine all this hydrogen right here is used up. If all that hydrogen is used up, then nothing is stopping this core from getting even smaller, right? That means if that core gets even smaller, think about, oh, that's a bit too small right here. All this helium right here, about this size, gets compacted down to something about this size. or even smaller, right? Something more accurate might be this small, right? If it becomes that small, if that core becomes that small, then it becomes hot enough to start fusing. Helium begins to fuse. Helium fusion. And this is what happens once you reach, let's say, 100 million degrees Celsius. When you become that hot, then helium is able to fuse. And remember, the reason why it gets smaller is because, as you run out of hydrogen, you don't have enough pressure to push out on the core. Gravity causes the core to collapse and collapse and collapse. And as it collapses, it becomes hotter and hotter. And eventually, that helium that used to be in that deposit is now able to fuse. And now that helium is fusing, and you still have that shell of hydrogen. So hydrogen shell fusing. So helium fusion and hydrogen fusion going on at the same time. And this stuff is still all hydrogen, right? But it's just not hot enough to fuse. So that's what our giant is starting to look like. That's what our star is starting to look like. And as this becomes hotter and hotter, right, as this hydrogen shell over here, this hydrogen shell starts to fuse more and more, it also deposits more helium for the core to use. So our helium core also gets bigger. So now it's about this big. And our hydrogen core also gets bigger. So our hydrogen shell. And the reason for that is because as you fuse more and more helium, then you generate more and more energy. The star becomes even hotter, the core becomes hotter, and therefore more and more of the star's hydrogen is added to the shell. So this is kind of what our star looks like. So we start at a normal main sequence star, right? It has a core, it's fusing hydrogen, it's all doing fine. And as it continues to burn through its hydrogen, it starts to deposit all the helium that it's been fusing and turning hydrogen into at its very core. But still doing okay because there's still all this hydrogen that's burnt that I can go through, all this hydrogen. What, 2 in the waiting room? All right, hey guys, we're going through the next phases after what happens in the main sequence. So we're talking about how this is a normal main sequence star and how it's fusing hydrogen inside its core, it's doing well, and it's depositing all of its helium in the center of the core. And as it continues on, you see that the hydrogen core starts to run out. You start to run out of hydrogen inside the core, and that's why the core begins to shrink. It doesn't have enough pressure to push out against gravity, and gravity starts to make the core even smaller and smaller, make it denser and denser and hotter. As a result, once the core gets hot enough, the hydrogen around it, like here, forms what we call a hydrogen shell. The hydrogen shell then starts to fuse hydrogen, and that's why the star now gets bigger. Right? You can see there's a noticeable difference between these two. What continues happening is that helium gets compacted more and more and more since the hydrogen is running out. And then it gets compacted enough, becomes dense enough that the helium begins to fuse. And once helium begins to fuse, then the star becomes a lot bigger because helium fusion generates a lot more energy. And your hydrogen shell gets a lot bigger because the core is now a lot bigger. So this is about 100 million degrees Celsius. And this is about 10 million degrees Celsius. So the core becomes really hot, right? And as this hydrogen shell continues to fuse, it deposits its helium at the core. So the helium core now goes from this size, from here, down to about this size. It becomes much bigger. And that hydrogen shell also increases in size because with more helium, you fuse more and more, you generate even more energy and become even hotter. So our star grows and grows even bigger. So let's kind of track. So on our right here, we have our HR diagram. And basically, I'm gonna label each one of these. Let's call this A, B, C, D, and E. Let's put E over here. E, all right? So A is our main sequence star. A goes right here. So since it's still burning and fusing hydrogen, is doing completely fine. It's not running out anytime soon. B is about what happens here. At B, you're starting to run out of hydrogen. You have a lot of helium in the center of your core and you're starting to run out, but you're still doing fine until you reach C. Once you reach C, this is where you're on what we call the subgiant branch. This is when you're really starting to run out of hydrogen and the core really begins to start collapsing. And as a result, that core starts to shrink, that hydrogen shell gets formed, and that creates more fusion all throughout the star, making the star even bigger. And since the star gets bigger, the surface is now further away from the core, and the surface becomes cooler. And since the surface becomes cooler, then the surface temperature of the star decreases. Once the surface temperature of the star starts to decrease, then it has hit D. The D point is where that helium has become so hot and so compacted that helium begins to fuse. And once helium begins to fuse, then it will continue, that hydrogen shell will continue to deposit helium at the core. The helium core gets bigger, the hydrogen shell gets bigger, the whole star gets bigger as it's fusing more and more stuff. And that's when it continues up this red giant branch. So throughout this entire red giant branch, so E is somewhere here, the entire red giant branch is fusing helium. No longer fusing hydrogen in its core, it's fusing helium. So that's the process from how a main sequence star becomes a red giant. It stops fusing hydrogen, core collapses, becomes hot enough to fuse helium, and then it becomes a red giant. Let's see what else. Okay. So basically, from here, if you see that path from before, right? This is the same path that we had from before, right? This is our main sequence. This is our A, our B, our C, D, and our E, right? It's the same HR diagram that we just saw. But from over here, have basically main sequence stars with 2 times the sun's mass, 3 times, 5 times, 9 times, 20, and 60 times the sun's mass. And you can see their paths are much weirder, right? They're much weirder. And I'm basically going to be trying to explain that. So let's imagine this is a star, maybe, let's say, 5 times the sun's mass. Let's say 5 times sun's mass. So if it's 5 times the sun's mass, then you still have your main sequence star, right? And this is in main sequence. It's still burning hydrogen. It hasn't run out of hydrogen yet. It's going to develop a hydrogen core, like so, and create a helium core and have a hydrogen fusing shell, like that, right? But since this star is so much bigger than the sun, it has 5 times the sun's mass, it's really, really, really massive, and therefore it has a lot more heat, has a lot more density than our own sun. And as a result, it can easily fuse helium. And what happens is that helium starts to fuse and it deposits carbon. So let's leave carbon as black. It creates a carbon core. That it deposits all the carbon in the center of its core, and it creates a helium shell around it. And outside the helium shell, you have a hydrogen shell, like this. So helium fusion going on here. This is all fusing helium. You have hydrogen fusing here. This is all fusing hydrogen. And now you see how our sun is kind of like an onion already. Yeah, Brayden? You had your hand raised for a while.
Is this how a black hole forms?
Yeah, so basically we're leading up to that, or we're leading up to what happens when you have a really, really big star. And this process of where you fuse heavier and heavier elements, when you're able to fuse helium and fuse even heavier elements, that's what leads you to a black hole. Yes. And we're going to get to that. So now you have as I said, a really, really dense carbon core, helium fusing shell, hydrogen fusing shell. And if you imagine that it goes even further, if you can fuse carbon, if this star is big enough, then it can even fuse carbon, starts to deposit nitrogen, and then it creates a nitrogen core. And then it has a carbon fusing core outside of it. And outside the carbon fusing core, you have a helium fusing core. And outside that helium fusing core, you have a hydrogen fusing core, like this. So that's why the star keeps on getting bigger, right? It keeps on getting bigger because you have so many more places to fuse, right? You're fusing carbon, helium, and hydrogen. And that's a lot more pressure pushing outwards against gravity. That's why the star gets bigger. So let's follow our number 5 here, right? So let's label this A, B, C, D. So our A over here is our normal main sequence star, right? We have B, which is when it begins to start fusing helium. Starts fusing helium here, B, right? Because it transitions over, or no, it should be here. This is B, right? Because the star gets bigger, right? You can see that this temperature where it was at A is now much cooler when it was at B. If it was at maybe 20,000 degrees Kelvin or Celsius at the surface of the star as a main sequence star, now when it transitions to a red giant, when it starts fusing helium, the surface temperature gets cooler because the surface is much further away from the core. So that's where B is. And then we have C. C, the star becomes even bigger. So therefore, C is about here. Right? It becomes even bigger. That means the surface is even further away from the core, and therefore becomes much colder. And the reason why we keep ascending, as you can see, this trend line goes like this, why this is on the luminosity scale, right? The star gets brighter because you have so much more fusion happening, right? If you look at B here, B, you have helium fusing and hydrogen fusing. C there, you have a carbon and helium and hydrogen fusion, so it keeps on getting bigger and bigger. And now D is going to be about here, where D, it becomes even hotter, even bigger, and the surface gets even further away and even brighter, right? So that's what this HR diagram is kind of showing us. At what points is the star burning what? So at A, burning hydrogen, B is helium, C, carbon, and D, nitrogen. And with even bigger stars, you can see how it's kind of, with just 5 times the sun's mass, you see how this path is kind of winding back and forth, right? Each time it's burning a different type of, a different atom, a different element. When you get to really, really big stars, they're going back and forth all the time, like that, because they're so big, they can easily burn hydrogen, helium, carbon, nitrogen, oxygen, all the way up. And look at this, right? You can see how they're going back and forth. It's all crazy. So really big stars can go through this process really, really, really quickly. Actually, let's see. I want to go with this. Okay, so going back to our own sun, right? So maybe in about a couple billion years, our own sun is going to look like this, like E over here, where you have a hydrogen fusion core, a really big helium fusion core, a big hydrogen shell around it. But what happens is eventually we're going to run out of hydrogen. This helium core gets really big, maybe about this big, right? But even though it's this big, there isn't enough mass there to start fusing carbon. So that carbon core is going to be right here in the center. And the issue is that if we don't have enough mass to start fusing carbon. And as a result, if we run out of helium to fuse, we can't fuse carbon, then there's no more outward pushing force. There's nothing more that's generating fusion inside our star. There's no helium fusing, there's no hydrogen fusing. There's just a dense block of carbon in the center of our star. What happens next? If there's no more fusion happening, that's what leaves us with what we call a planetary nebula. If there isn't enough mass to fuse that carbon, the nitrogen, that oxygen inside the center of its core, then the outer layers of the sun they just gotta blow away. There's nothing else holding them there. There's no more fusion happening. The star is basically dead. The outer layers of the sun just start to float away into space because it still has a magnetic field. So it kind of blows it out as solar wind and it releases it into space. That's what a planetary nebula is. So a planetary nebula, these kind of look like explosions, right? Here's the Cat's Eye Nebula, right? Or these over here, they kind of look like explosions, like something like blew them apart, but not really. These layers of the sun just started floating off into space as there was no more fusion happening. So not really an explosion, just a gradual process of the sun dispersing throughout space. So that's what a planetary nebula is, the death of a star. And in the very, very center here is our core. That's our core of carbon, our core of nitrogen, or basically the last element that our sun couldn't burn up. Yeah, Brayden?
Why is it called planetary if it's the death of a star?
Yeah, I looked into this for a long time. I couldn't really, basically some guy just called it planetary because they thought that it was a planet inside the very center, but they were wrong. So the word planetary is kind of misleading here. Doesn't have anything to do with planets. All right, but from there, yeah. So that's a planetary nebula, death of like a normal low mass sun-like star. All right. So this is what I call like the life cycle of the sun, right? I want to kind of put into perspective how long our sun has left to live and how quickly red giants appear and disappear, right? So our sun here, or our sun used to be a molecular cloud, right? Like this, and it collapsed, turned into a protostar, and became main sequence. After it became main sequence star, look how long it stays as a main sequence star, right? It stays as a main sequence star for basically 9 billion years of its life. Right? That's a really, really long time. And slowly throughout this process, as you can see, the star getting bigger and bigger, that's because it's starting to run out of hydrogen. As it runs out of hydrogen, that core collapses a bit, and then it starts to create a hydrogen fusing shell, which causes the star to get a little bit bigger. That's why you see throughout this process, the star is starting to get a little bit bigger like that, if you notice that. And then suddenly it becomes a red giant, because at that point, it completely runs out of hydrogen in its core. Now it's fusing helium. It grows really, really, really big into a red giant. But the issue with it is that red giants are really unstable, right? Because you're fusing helium, that's much more difficult to fuse in hydrogen. It's going to burn a lot faster and a lot hotter. So our red giant becomes really, really big, but then it's very short-lived. Eventually, a planetary nebula happens. It stops fusing helium, and the outer layers are blown off, and it becomes what we call a white dwarf. That's that thing right in the very center here. That little dot, that really bright white dot, that's the core of the star. That's that dense, core of hydrogen or of carbon or nitrogen or oxygen. That's what we call a white dwarf. That's the last bit of the sun, the core of it. And it remains a white dwarf for basically the rest of its life, cooling down until it disappears. Yeah, Braden?
How does it not instantly disappear if it's not fusing anymore?
Yeah, well, because remember, the core is still super hot, right? It's at least 100 million degrees Celsius. That's really, really hot. Even though the rest of the layers of the sun, go away, it's going to take a long time for a star or the core to go from 100 million degrees to nothing, right? To basically the temperature of space. So it takes a really long time to do that. Yeah, so that's why it's still really bright, right? It's called a white dwarf because it's still releasing all that energy, all that heat as radiation and white light. So as you can see here, you see how this is really bright right here. That white dwarf is really bright, but eventually starts to cool down. As you can see, it's less bright and less bright. It becomes darker and darker. That makes sense?
Oh, yeah.
All right, cool. All right, so the last bit is basically the supergiants, right? This is what happens once at this cutoff point here, or this cutoff point here, is when they transition into a supergiant, right? Supergiants are able to fuse those heavier elements, able to fuse carbon, able to fuse nitrogen, and things even heavier, like oxygen and silicon and neon and stuff like that, right? So remember that those shells that we saw from before, right? We have an iron core with a silicon shell, an oxygen shell, a neon shell, carbon fusing shell, hydrogen fusing shell, and helium fusing shell. So that's what I meant by these bigger stars kind of look like onions when they turn into giants, because you have all these different shells fusing different types of atoms. That's what a supergiant looks like at the end. But the issue with a supergiant is that it can only fuse up to silicon. You can't fuse iron. And the reason for that is that it actually takes more energy to fuse iron than it is than the reaction releases. right? Because the reason why hydrogen is able to fuse into helium and release so much energy is because it takes less energy to fuse, combine those hydrogen together than it is that it releases. So basically, you can't fuse iron. You can't fuse it. So what happens after you reach iron? Once you get this iron core, you start to run out of places to go. If you run out of that hydrogen, run out of this helium, imagine if you start running out of all these different elements. If you run out of all these elements and everything becomes carbon, then you have so much mass, right? You're talking about maybe trillions of kilograms of mass, trillions of kilograms, right? That's literally like 1 and 0, 0, 0, 0, 0, 0, 0, 0, 0. What is that? Million, billion, another kilograms, right? That's a lot of mass. And if you have that much mass, that's what's going to end in a supernova. If you look at that, if you look at A over here, right? A here is showing that that iron core. Once you have that iron core, there's nothing pushing out, right? Everything is collapsing into the iron core because you have trillions of kilograms of mass all pushing in on just a little bit of iron. That's a lot of pressure. So it causes it to collapse further and further and further until even the atoms themselves break apart and like get smushed together. All the protons, the neutrons, and everything are split apart and like stuffed against each other as close as possible. Eventually, you hit a certain point, right? Shown in the red here. Basically, what that point is where you compacted stuff as much as possible. I don't know if you ever any guys have like, I don't know, I've played with like metal balls or whatever, right? But if you like put them all in a container, right, and you throw something against it, it kind of bounces. It acts as a solid surface because it's so compact that it's not going to shift around at all. So that's what this red is showing. It's so compact, it becomes a solid, a complete solid bit of like iron. And all this these black arrows are all the mass hitting that red surface. As it hits it, it bounces and it creates what we call a shock wave. It becomes a shock wave like that. And that shock wave in the red expands further and further and further. As more and more mass hits it, that just makes the shock wave go even bigger and bigger. So that shock wave starts from the core and it expands out through the entire star. And that's what creates the explosion. So the supernova is an explosion where all the mass in the star collapses down to one point. It reaches that point of like where even the protons and neutrons are squeezed together, what we call degenerate. That's what we call degenerate. And then creates a shock wave and boom, explodes. I should find some pictures because supernovas are really cool. Supernovas. Well, some of these are like fake. Like this is fake. This is what we call an artist's depiction. The reason for that, this is just some artist decided to draw it. We don't actually have a photograph of it. Someone decided to just drew it. But this is real. This is a real explosion, right? If you look at this explosion, it's really different from our nebula, or our planetary nebula here, right? This nebula, you can clearly see the layers, right? This is our hydrogen fusing shell. This is our hydrogen that wasn't ever burning. The same thing here, you see that hydrogen fusing shell and the different layers of the sun. It's really clear, it's nice and peaceful. Because remember, in the nebula, everything kind of drifts away. There's never any explosion. But you look at this supernova, it's really chaotic, right? Stuff is flying all over the place. You have these tendrils going through these filaments pointing here now. You have massive caverns of random space and gas and light, because it's a really chaotic thing that happens. Let's see other good pictures. Or like this, right? It looks like a giant bubble of just stuff that just exploded out. Or here, right? This isn't really uniform at all, right? There's no symmetry in it or anything. Or look at this, right? Right there in that center, that's probably a black hole. This was a really, really big star that turned into a black hole. And now this is a supernova that's all around it. Here's another look at it, right? Or something like this. This one's pretty cool, right? This is close enough to a real image, but you can see that explosion, right? Where it's really chaotic. Like look, this is so fake. This is so fake. This looks like the animation of the Death Star exploding, right? These are all really fake. Or like this, very fake. Let's see if we can find some better ones. There's Crab Eye. See that it says artist's impression, right? Look how perfect the supernova is. Look how perfect it is. There's no way a supernova could ever look this perfect, right? Because it's not, yeah. That's why it's an artist's impression, not real. Yeah, I think that's about it. So yeah, that's where we end off today. But I do have like one Kahoot we could do if you wanted to try. How does the class feel? Do you want to try Kahoot? All right, how about I just get it started? So I have to log in. All right, I'll play as guest. Classic. All right. This will be the last thing. I think it's about 15 questions, I think. So it's pretty short. All right. Got Braden, got Timothy, got Austin. All right. Isaac, Jason, Yona, and Yoming. You guys want to join? All right, one more. All right, got it. Let's go. Which of these stars is the oldest in terms of its lifestyle? You don't worry about the picture. Yeah. Right. So remember, the thing here was that red giants are, in fact, that's what we spent the most of the time today. We didn't on today, right? They definitely are older than main sequence stars. But remember, after a red giant, I know we didn't touch on it a lot today, but after a red giant explodes and leaves, or not explodes, but becomes a planetary nebula, that center, that core, is that white dwarf, right? That's the super hot, 100 million degrees Celsius core is. That's what we call a white dwarf, right? All right, next. Yeah, right? The sun is still burning hydrogen as its main source of fuel. The red giant, it's kind of a bad question. The question should be, which type of star is burning hydrogen as its main source of fuel? Because those who answered red giant, you are correct. It is burning hydrogen as a fuel, but just as its outer shell, right? It's not its main source. So I think that if you answered red giant, you're still correct. Right. Remember, the sun is burning hydrogen and is depositing helium in its core. All right. Red giant, that's correct. It's burning helium as its main source of fuel. White dwarfs, um, white dwarfs are they're no longer burning, right? That's what happens once you run out of things to burn, and that's why it releases itself as a nebula, because there's no more things to burn. So therefore, it can't burn anything. And a blue star, I'm not exactly sure. I didn't make this Kahoot. I just thought it was okay. But I believe a blue star, what they're trying to say is a really big O-type star, like a really blue, a bright, big star. And these questions really aren't good. These questions really aren't good. This is my bad. I should have given us something better. But I'll try to explain the answers as best as I can. Yeah. So when a star like dies, basically what that means is that we can no longer detect it with our telescopes, because it's no longer hot enough to give off any sort of radiation we can see with our telescopes, right? Because we see things with light. So a white dwarf is still bright enough for us to detect, because it's really bright. It's giving off a lot of light. So that's the closest to death. As it cools off, then it will begin to die. Then red giant comes before white dwarf, and a sun comes before that. So the order goes from sun, red giant to white dwarf in terms of youngest to oldest. And a red dwarf, well, that doesn't exist. So I'm glad no one chose that. This time this graph might help a little bit. Right? So luminosity, right? How bright a star is. So a white dwarf, while it certainly is bright, the thing is that there's no more fusion happening, right? There's no more fusion happening, so it can't create its own energy, basically. Red giants, however, remember they have a helium fusing core and a hydrogen fusing shell. That's a lot of fusion happening, so that creates a lot of energy and a lot of light. So that's why red giants are the brightest a star will ever get. Our sun is going to become a red giant and become even brighter than it is now. All right. So that's why red giant is the correct answer. Yeah. This question is also whoever answered square, I appreciate it. But this question is really weird. Let's see. What causes a star with the highest luminosity to be the brightest? These are the same thing. Luminosity literally means brightness. That's a really bad question. But what causes a star to be the brightest is its size. Yes. Because the more mass you have, the hotter the star is, and therefore, well, the brighter it is, right? The hotter something is, the brighter something is. Yeah. So surface temperature, I don't know. It's this question's really bad. But yeah, just remember the bigger a star is, the brighter it is, the hotter it is, right? Lowest luminosity, yeah. I was gonna repeat one more time. Remember, a red dwarf doesn't exist. That's just a made up thing that for someone made in this Kahoot. Lowest luminosity is the white dwarf. I guess this time the graph would have helped. So this is an HR diagram, right? So this shows our sun right here in the center. Remember, it goes on that weird path to become a giant, right? It becomes a giant star. And after it enters a planetary nebula, it comes down here to become a white dwarf, right? Where its surface temperature is really hot, but it's not really bright because it's no longer burning anything. So yeah, that's why the white dwarf has the lowest luminosity. Yeah, same thing, right? Size. Remember, size, heat, size, and brightness are always linked together. And this graph might help. Surface temperature is on the bottom, right? Yeah, white dwarfs, right? So even though red giants and stuff are much hotter at their core they're hotter. At the surface, they're much colder because the surface of a red giant is the furthest away from the core. So that's why, but white dwarfs, that's just the core itself. So the core is always really hot. So what fuel does a main sequence stars? Yeah. So it should be hydrogen. Because a main sequence stars are like our sun right now, right? Our sun is currently burning hydrogen. And as it runs out of hydrogen, that's when it transitions into a red giant. So red giants are the ones who are burning helium. But this is also kind of unfair because some main sequence stars do burn carbon. Yeah. So again, like we dived much more in depth into stars. So that's why these questions are all like they're really simple. They don't really talk about the details about what happens in a star. So I think that helium, carbon, and hydrogen, they're all like correct answers because some main sequence stars do burn helium and carbon. If they're big enough, of course. Yeah. So I guess they're kind of tricking as well because like a red dwarf isn't a stage, right? Like it's not really a stage, so I guess it's not represented on the diagram. But the for sure answer is a black hole because a black hole, like you can't put it on the diagram because we don't know if it has a temperature, we don't know if it has a luminosity, right? So that's why it can't be represented. But a white dwarf is represented on the diagram, right down, all the way down here at the bottom here, where it has really low luminosity, but it's also pretty hot. So a white dwarf is represented. Yeah. All right. So I guess again, the structure of my lesson wasn't perfect. I wanted us to spend like learning what a red giant was. So for most stars, like of low mass stars, stars like our own sun, they're not what we call massive, right? They're low mass. And the reason for that is because, yeah, massive stars are really rare, basically. So that's why I wanted to focus on like sun-like type stars. And for sun-like stars, after they become a red giant, they become a nebula, right? But for really, really, really big ones that can fuse silicon all the way up to iron, right? Those ones will end in a supernova. So that's the difference. Massive stars end in supernova, and low mass, like normal stars, end in a nebula. I'm so confused. This red dwarf, okay. This is, what is a red dwarf? I'm so confused. A red dwarf doesn't exist. It's a TV show. What is this Kahoot talking about? All right, forget this question. This Kahoot's going crazy. All right. The life cycle of a star depends on its right? So everything depends on mass. How massive a star is determines how gravity affects it. If it's a really big star, then the gravity will compact it together, making it more dense, hotter, right? And also, since it has more mass, it'll have more volume. If it has less mass, then gravity doesn't have as much effect on it. So therefore, it reduces its density isn't as great, its temperature isn't as hot, and therefore it has less volume. Everything depends on mass. Remember, everything comes from those molecular clouds, right? So depending on how much mass was in that molecular cloud determines how big the star is, how hot it is, and how dense it is. So everything depends on mass. So these are all correct temperatures. They do affect a star's life cycle, but mass is what determines it from the very beginning, all the way back to when it was born, basically. Yeah, there we go. So main sequence, right? Main sequence stars where the biggest are always the brightest and always the bluest. So yeah, that's all the way here in the corner of the HR diagram, right? You see it all the way up here, right? So that's our really, really blue stars. Those are our biggest. So yeah, that's that. There's no such thing as a red dwarf. This Kahoot's going crazy. I don't know. The correct answer should have been the sun. Yeah, so there are obviously going to be only two real answers to choose from here, either increase or decreases, right? Because everything depends on the mass. So let's let me draw this out just a little bit. So let's imagine, let's have a graph here. It's like this. Let's say fusion rate, temp, right? The temperature of the core, temp core, and lifetime, and time. So let's for a low mass star, it kind of looks like this, right? The core will get hotter and hotter and hotter, and it'll burn more and more and more, but it'll never burn that much because it doesn't have enough mass. So this is low mass. But for a really big star, however, that curve looks more like this. So massive. Since a massive star is so much bigger and so much hotter, it can burn a lot of fuel, a lot more fuel at the same time. So it runs through its fuel much faster than a low mass star. So a low mass star like our own sun might last for maybe 10 billion years, basically. A massive star might only last for 1 billion, right? Just because it burns through all its fuel much faster. So that's why the life expectancy of a big star goes down. All right, 3 more questions. What? Oh yeah. Yeah, main sequence, right? Because everyone's pretty young. You only become a red giant when you're like 100 years old. So, yeah. 2 more. So yeah, this is also something because we didn't have enough time to go over white dwarfs today. But basically, it's true that like from what we know, right, from a protostar to main sequence to a red giant, main sequence is most of its life. But a white dwarf, it just sits there and cools down for the rest of its life. So until it dies. So the technical answer is, I don't know. The technical answer is white dwarf. So you guys should be right. But it's also true the main sequence is a little like, again, it's a difficult question. But we'll definitely talk more about it in the next class when we talk about white dwarfs, black holes, and neutron stars, stuff like that. All right, last question. Yeah, that's 10 billion years, right? So that's about how long our sun has to live. I know it's really difficult because like this is like, when I first saw this, I thought the answer was going to be the blue, because I thought that was 1 billion, but that's actually only 10 billion. So yeah, this is the correct answer because that's 10 billion years. Yeah, so our sun's going to be around for a very long time. All right. So yeah, that's so this was a pretty bad Kahoot with some really suspicious answers. Like what is a red dwarf? That doesn't even exist. But yeah, good to see you guys learn something, and I hope that you guys will join me next class as we learn about the rest of the stellar life cycle. We dive into black holes, neutron stars, and white dwarfs. All right, sounds good. All right, and see everyone.